In section 8.3, we look at a seemingly easy computation called the dot product. So the dot product is going to be a computation that you apply to a pair of vectors. So we'll start off with a definition. Suppose that you have two vectors. Let's call it vectors u with components u1, u2, u3, and v made up of elements v1, 2, and 3. The dot product of u and v is the real number given by the following computation. So u dot v is equal to u1 times v1 plus u2 times v2 plus u3 times v3. So you just take the corresponding elements, in this case the x elements, multiply them together, the y elements, multiply them together, the z elements, multiply them together, and then you add those products together to get the dot product. As easy as this computation is, it is fundamental in really cracking some of the really hard questions and problems that we find in 3 dimensions. So let's get acquainted with the dot product with a quick computation. Suppose we have two vectors, u made up of 1, negative 2, 5, and v made up of 3, 1, 4. The dot product of u and v is equal to 1 from the first vector times 3 from the second vector plus negative 2 from the first vector times 1 from the second vector plus 5 from the first vector times 4 from the second vector. So that's 3 minus 2 plus a 20. You got yourself 21. So the dot product between u and v is equal to 21. Here are some nice properties for dot products. These properties are going to come in handy when we're developing computations or when we have computations involving some weird numbers with fractions or radicals. These properties are really going to come in handy to simplify our work. So suppose that you have 3 vectors, u, v, and w. And suppose that c is a scalar. For our purposes, whenever you're told that something is a scalar, you can think about a real number. In other classes, a scalar can be allowed to be a complex number. So the following properties are true. One, when you have a vector dotted with itself, it's equal to the length of the vector squared. So this is making a statement about how you can take the dot product and convert it into something involving a length. But on the flip side, we can say that this statement is the same as saying that the length of a vector is equal to the square root of the dot product between the vector and itself. I like to imagine that this is creating a bridge between lengths and dot products. So whenever you need to go back and forth between any of these structures, you can use this property to do that. We'll be using this later on when we apply the law of cosines to come up with a really nice property between the angle between two vectors. Property 2. The dot product is commutative, so it doesn't matter whether you take the dot product of u and v or v and u, you would get the same thing. In our computation above, when we took the dot product of our 1, 2, 5, 1, negative 2, 5, and 3, 1, 4, we would get the same thing if we would switch the values of these pairings, right? Or in other words, if we reverse the roles within the dot product computation. So u dot v is equal to v dot u. Property 3 states that the dot product has a commutative property. So if you're taking the dot product of u with the sum of v plus w, you could imagine that you distribute the u through these two vectors and get u dot v plus u dot w. So again, here's the distributive property of dot products. For property 4, here we have a statement about what we can do when we have a scalar multiple involved within the dot product computation. So suppose that you have u dot v, but the first vector u is multiplied by a scalar. You could factor out that scalar right out and just focus on taking the dot product of u and v. This property also works if that scalar is being applied to the second vector. And if we have u dotted with cv, you can factor out the scalar to the very forefront and focus on a potentially simpler computation of u dot v. So as an example of this, consider if we had to take the dot product of, let's say, 1 over 7, negative 2 over 7, 3 over 7, with square root of 2, negative square root of 2, and 3 square root of 2. This first vector is like the vector 1, negative 2, 3 if I were to multiply this vector with the scalar 1/7. This vector radical 2, negative radical 2, 3 radical 2 is like the vector 1, negative 1, 3 if I were to multiply it by the scalar radical 2. From this first vector, I'm going to factor out a 1 over 7. From the second vector, I'm going to factor out a radical 2. And left behind, I have the vector 1, negative 2, 3 dotted with 1, negative 1, 3. So the numbers left over when I do this kind of factoring are a whole lot easier to work with. So I would have 1 over 7, radical 2, and then the value of the dot product would be 1 times 1 is 1, negative 2 times negative 1 is positive 2, 3 times 3 is 9, so you got yourself a 12. So that's 1 over 7, a radical 2, and a 12. So I think you can agree that factoring things out really does make things a lot more efficient. And let me tell you, sometimes within certain computations, you have a whole lot of dot products that look like this. So factoring out as many of those scalars that make things a bit of a drag really goes a long way on making this kind of problem really efficient. And finally, property number 5, when you take the dot product of a 0 vector with any vector, that's going to give you 0. So again, in this case, the 0 vector is going to be the vector 0, 0, 0. And taking the dot product with any vector u1, u2, u3 is going to give you the 0 real number. Keep in mind that this 0 and that 0 are two different animals. This is the old-fashioned 0 that you see on the real number line. This is a vector, 0, 0, 0. Keep that in mind because some computations do have both of these floating around, and depending on which one you use, you could be making a mistake in structure.